All right, introduction to integrals. Since the beginning of the school year, what we have done is we have learned how to take an original function and we have found the derivative of that function. So now what we're going to do is we're going to figure out, giving a derivative, how to go backwards. Or in other words, in calculus, we say how to find the antiderivative of it. All right? So we're going to start with some baby problems, and then we're going to go into notation, because the notation gets a little bit messy, and then eventually we will get to use this symbol right here. From now on, we are going to be using this symbol a lot until the end of the year. This represents many concepts. We're going to put some numbers right here on the lower bound and the upper bound. We'll put some functions in here. We're going to do it with graphs. Then we're going to do it with approximations also. All right? But we're going to take it one step at a time. For right now, the only thing that I'm concerned with is, do you know, giving a polynomial, and if I call this the derivative, do you know how to go backwards? And then on the future lessons, we're going to go into the other concepts. Okay? All right, so let's say that you're giving a derivative, and I'm calling this derivative right here 5x to the fourth. Is there a way for you to figure out what the original function is? What process do you have to go through to figure out its original function? You know what I'm asking? So in other words, typically what you do is, I'm just going to make up a problem right here. And I'm going to call this one's originals and this one's derivatives. Okay. So let's say that I'm giving you an f prime of x, and let's call this one 3x squared. Now what would you do to go back to the original function? Well, typically, if f of x equals x to the fourth, and I ask you for the derivative, what is the process that you go through? 4 times 1, and then take away 1, right? So you'll say 4 times 1 is 4. So what you're really doing, you're actually multiplying. That would be your step 1. And then you're taking away 1 from the exponent, so you're really subtracting. So your step 2 is to subtract. So now what you really want to do, if you want to go backwards, you have to undo the subtraction, and you have to undo the multiplication. And you have to do it in this order. So in other words, for the antiderivative, what you have to do now is you have to add. And then after you add, you're going to have to undo the multiplication, and the opposite of multiplication is division. So this would be your step 1, and this is your step 2. Is that a phone? So that is the process. We're going to have to add, and then we're going to have to divide. And I decided to give this a name. So you're going to hear me say in the lectures here to bump up and divide. So when I say, did you bump it up and divide it? What I'm really saying is, did you take the antiderivative of that, giving a polynomial? So the bump up part is really the add, and then the divide, obviously, is just divide. Okay? So let's practice a little bit with this, so that we can get our feet wet with this. So given 3x squared, bump up, so you bump up the exponent, so that becomes x cubed. You added 1 to it. Now remember, you do have this 3 in front of it, so leave it alone. It's already there. After you bump it up, and then you're going to have to divide by 3. Those cancel, so your final answer is x cubed. And we have to call, because this is f prime and we're going backwards, we have to call this one f of x. So far so good? All right, let's try one more. F prime of x equals negative 2x to the fifth. So let's bump it up. x to the 6, the negative 2 we leave it alone. We have to divide by the number after we have bumped it up. Not the 5, but the 6. So my final answer is minus 1/3 x to the 6. And this is going to be called f of x. So far so good? Let's say that I have an f of x, original function, I'm going to be going back and forth, equals 3x squared. What is the derivative of this? 6x, right? All right, let me give you another original. F of x equals 3x squared plus 8. What's the derivative? 6x? What if f of x equals to 3x squared plus 10 to the 6? 6x. So do notice that these are numbers. I can have a negative right here, I can have a fraction, but as long as it's a constant, and this right here is the same, its derivative will always be the same, right? So that means that if I give you a derivative that looks like this, and then I ask you for the antiderivative, which antiderivative are you going to give me? You're going to give me this one, or this one? Or many other ones. We actually have an infinite number of antiderivatives. Which one is it? We need something to represent these numbers here, right? Now, you're not going to put 8x right here because then the derivative would be 6x plus 8, right? Whatever. So these have to be constants. So what we're going to do now is if I give you something that looks like this and you're doing its antiderivative, then what you'll have to do is, given f prime of x equals 6x, antiderivative, you will give me f of x equals 3x squared because you did the bump up and divide, but you're going to tag along a c on it. This c is representing all these numbers right here. Every time you do an antiderivative, we tag along this c right here. And then in the future lessons, I'm going to teach you how to figure out what the c value is. So an antiderivative spits out a family of functions. Spits out this one, this one, this one, this one, many, many, many functions, all of them, because of that constant. Capiche? Derivative equals negative 2/5 x to the 1/2. Same idea, but I'm throwing in some fractions in there to see if you can go through the process of bumping up and dividing. All right, let's bump up. So in the beginning, we're probably going to write little numbers right here to help us to do the bumping, kind of like what we did with the derivatives. Eventually, we're going to do that mentally. So we can cover this right here. We can add 1 to this, so you're going to imagine a 2/2 right there. So eventually, you will get x to the 3/2. So you'll have x to the 3/2. That's just the bumping part. Now remember, you do have this negative 2/5 right here. You are going to divide by that right there. So divide by 3/2. But in order to simplify this, a fraction over a fraction, you must convert this into a multiplication. So it's the same thing as flipping the bottom fraction. So it becomes a negative 2/5 times 2 divided by 3. And that is the same thing as just grabbing that and flipping it right here. All right. So eventually, we're not going to do this right here because we were going to do this so much that we're just going to say, oh, copy this, move it to the side, grab that number after you have done the bumping up, then flip it and put it here. Okay. So that would get me a negative 4/15 x to the 3/2, and that is my f of x plus c. Right? I call this c chucklehead. So don't forget the c, because if you forget the c, then you are a chucklehead. F prime of x equals square root of x cubed. All right, let's knock this one out. Rewrite the problem as x to the 3 halves. Because you can't do anything like that with square roots. We've done this before, right? So let's bump it up. So we see a 2 right here, so this becomes x to the 5 halves. And we have a 1 right here, so we're just going to flip it so it's 2/5. And this is my f of x plus chucklehead. You forgot to see, huh?
No, I'm just saying it's so funny to see that, like, and then you put the chucklehead.
Oh, yeah. Yes, good. All right, rock on. All right, so now let's play with notation a little bit. So f prime of x equals 2x. F of x equals plus c. So far so good? So do notice that right here you went from little f prime, to little f without the prime, because you went back to the original equation. But what if, remember these are the derivatives, originals. What if I decide to call my derivative f of x, no prime on there? What are you going to call this one? Oh, x squared plus c, chucklehead. What are you going to call this? Right? It's like we're stuck now. We need something else, right? Because Flores decided to just start twisting the problem here, calling that one a derivative. So yes, you're absolutely correct. So we're going to call this one big F. So the antiderivative of little f is just big F. Well, you can't leave this floating here. You got to call it something, right? So if you have the function and you see no prime on here, and it's lowercase, then its antiderivative is going to be a capital. Right? So if I give you g of x equals 3x, its antiderivative, bump it up, divide, plus chucklehead, that's little g, then this is big G. Yes? Good? All right. Raise this.
Wait.
Watch the video. What if I call this one big F prime of x equals 2x?
Even bigger.
Bigger F? That waiting messed you up big time, boy. Oh, editing?
F double.
You're going backwards.
No, the big F.
It's just big F, right? Because you're just going to remove the tick marks, right? So it's just big F.
When did you start off? What's the derivative is big F?
So there you go, right? So we have, what do you notice right here, right? If both of these are big F's, they're the same functions, then wouldn't you agree that if you take the derivatives of these two big F's, their derivatives should be the same? And they are the same, right? 2x to x. So that means that these two are equal to each other. So bottom line is that big F prime of x is the same thing as f of x. Okay, so the functions that I have given you so far right here has been with notations that we have used before, with f's and little f's, and I now introduce the big F and the big F prime. But another way that you can be presented with a problem where you have to take the antiderivative is if they give you something that looks like this. See, there's no equal on here. Like on the other function, it had f prime of x equals 2x. Right here, I literally ask you in plain English, take the antiderivative of this, and that's where you got f of x equals x squared plus chucklehead. Same thing here. This is really asking you the same thing. Take the antiderivative of 2x. Now you might be thinking, well, where does that dx come from? Well, this is going to be explained in the future lessons. It does have some meaning, but for right now, for this lesson, just understand that this symbol right here is their way of saying take the antiderivative of that. So you take the antiderivative of that, and you will get just x squared plus chucklehead. So it's the same answer, just that one has an equal sign and this one doesn't. Clear? Okay. Y equals antiderivative of little f. So if you're going backwards, right, because it's saying take the antiderivative, and it's little f, and it has no prime, then the antiderivative is just going to be big F, and that's exactly what they're saying right here. It's big F plus the chucklehead. Big F prime, take the antiderivative, well, you just remove the tick mark, so the antiderivative is just big F also, plus the chucklehead. Little f prime, antiderivative, just remove the tick mark, so it's just little f. G prime, antiderivative, so it just becomes little g. PVA, S prime of t. Oh, you remove the what? The tick mark. So it becomes S of t. Now let's think about this a little bit more deep. What is S prime of t really?
V of t.
So I can put V of t right here, and what's the antiderivative of V of t? S of t. Right? But I did it with the tick marks on there so that you can actually see the relationship of removing that little prime from there. Here, what I'm giving you right here is our rules. Remember when we did limits? With limits, we also have rules that you can have a limit that you can split it into two limits. Well, it's sort of the same idea here. The best way to learn stuff like this is to actually do some examples. So I'm going to do a few right here. Antiderivative of 6x cubed dx. So you might be thinking, well, Flores, I can just do that on the fly. I can just wing it and bump it up and divide and come up with the answer. True, but I'm trying to teach you some rules here. So one of the rules is that you can move constants only outside of this symbol right here. So this becomes 6x cubed dx. Then you can ignore the 6, do the antiderivative of x cubed, and then multiply the final answer with the 6. And it would be okay. It would be equivalent as just saying bump up and divide this one. By the way, if you bump up this one and divide it, what's your final answer?
We have x to the fourth.
X to the fourth and divide it. Oh, you did it on the fly. Plus chucklehead. She forgot. So let's try it here. 6, leave it alone. Bump up and divide this one. So that becomes x to the fourth. Divide is 1/4 plus c. So this section right here is what's inside of the brackets. Simplify this. 6 and 1/4 is just 3/2 x to the fourth, and 6 times c is 6c. Are we okay with this so far? And you might be thinking, well, they're the same problem, so the two answers should be the same. However, physically, they do look different. Are they really different? Really not, right? You might be thinking, well, what if C is 5? Here would be a 5 and here would be a 30. Well, you solved the two problems in different ways. So this C has no connection with this C right here. So you cannot make that assumption. I could have called this one D, right? I mean, or E. That's fine. You say what? P? You say P?
No,
Oh, what do you say?
he said knucklehead.
Oh, knucklehead? Or B? That is funny. That is funny. Who would think of something like that? What about with the P? Poco head? I bet somebody there is going through the alphabet.
I like it.
Knucklehead.
I like
Mucklehead. Mocklehead? Edit? Alright. Edit video.
Oh,
Antiderivative of little f prime plus little g prime. Well, the antiderivative of little f prime is just little f. And for that one is just little g. So my final answer should be little f plus little g plus chucklehead. Well, there it is. Could be minus 2. And this is the rule for bumping up and dividing. It presented to you in a different way. So let's have you guys practice. And then we'll put the answers here on the board. Facebook? All right, let's write the answers for this. Antiderivative of, people say, do I just attach an x to it and be done with it? Yeah, that's a short way of doing that. But you can also write it as negative 5x to the 0, so you can actually see that you're actually bumping up. Bump up with 0 is a 1, so it's negative 5x. And then divide by the 1, so negative 5 divided by 1 is just negative 5, plus c. Pi is a number, so the antiderivative is just pi x plus c. Little f prime, so you remove the prime when you're doing the antiderivative, so this is just 5 f of x plus c. Bump up and divide, bump up the 2, it becomes a 3. Divide, 3 divided by 3 is just 1, so this is x cubed plus c. This is two terms. Do the antiderivative of this term plus the antiderivative of this one, and I think we have done them before. Oh no, that's a negative. The antiderivative of 4x cubed, x to the 4th, divide, 4 divided by 4 is 1. So there you have it. Antiderivatives. Let's try to do something that's more challenging. So we have those with radicals and ratios. Your turn? Or you want me to do them?
I want to try.
This try?
Yes. Okay.
Alright, integral of x to the 1/5 dx, antiderivative, bump it up. So I'm seeing 5 right here. So this becomes x to the 6/5. Divide, flip, 5/6. Plus chucklehead. Okay?
You guys do it.
X to the -5th, after you move this to the numerator, switch the sign on the exponent, dx, bump it up, add 1, -4, there's a 1 right here, and you divide, so it's minus 1/4. Plus, okay. Same idea here. move this to the top. Now you're not going to move the 5. The 5 is already on the bottom. So rewrite it as 1/5. You can even extract the 1/5 on the outside if you want. I'm not going to do that. Bump it up, x to the -2, and divide. This is the same thing as putting the -2 right here on the bottom. So it's -1/10 plus, check on here. So far so good? All right, a little bit of trig, and here's my recommendation. If you are good at having an original function and finding its derivative using trig, then when you're confronted with antiderivatives, what you need to do is you need to ask yourself, the derivative of what gives me this, whatever it's inside of the integral, right here. Another helpful hint is to have pist written somewhere, because with that one we can derive all the other connections for cosecant, secant, cotangent, tangent. All right. So let's go through the first ones. You know, the cosine and sine, they're pretty easy because they go back and forth, whether it's derivative or antiderivative. So the derivative of what is cosine? Sine. Okay. So sine x plus c, and I'm done. The derivative of what is sine?
Negative cosine.
Whoa. First period when? Write cosine, Mr. Flores, and then we'll go from there, and then we'll think, okay? All right. The derivative of cosine is negative sine, but this is positive sine, so I have to tack along a negative on there to cancel that negative. So if I were taking the derivative of this, you would say, keep the negative. The derivative of cosine is negative sine, so you have negative sine, and that will get you your positive sine that you want. Right? So that's the idea behind it. Secant squared. Well, we know that the derivative of tangent is secant squared. So the antiderivative of secant squared should be tangent. Let's check ahead. You can see the pattern here. You know, I put them in order, sort of. So that's tangent, so that's cosecant squared, so that should be a cotangent x plus c. But the derivative of cotangent is negative cosecant squared, so I do have to put an extra negative on there. And this one is pist, and this one is the one that's connected to pist. So the derivative of secant is secant tangent. And that's what I have right here, secant tangent. So that means this one better be secant x plus c. And this one is cosecant x plus c. But the derivative of cosecant is negative cosecant cotangent. And I have a positive here. So I have to tack along that extra negative on there. How we feel about this? So far, rock on? Let's see if there's something here. What time is lunch?
Right now.
Right now? No, really, is it 12:30? Okay. I have a long drive. Oh, the reason I don't have 40 is because there's a game.
Oh.
There's a tournament we're playing.
I thought it got canceled.
Yeah.
No.
Oh, you said it got canceled? Soccer?
No, because the temperature was fine, so they say what? What did you say, Rosa? Are you gonna play? So he's not teaching us because he's.
I said no.
Yeah, I'm gonna have to make it up to my fourth somewhere along the line. No?
No egg rolls.
Make it up.
Oh, you don't like egg rolls?
Make it up by bailing fourth period so that we can come second.
Really? You're the first person that I have met that doesn't like those. I'll give you some pho from Garland.
Yeah.
Oh. Oh. Ah, all right. Here, do not try to start taking the antiderivative of each term right here because this is a product. So we still don't know how to do antiderivatives of something that it's a product. So what we can do here is we can simplify this. We can do the distributive property and then go from there. Distributive property, 3 sine theta plus sine theta cosecant theta d theta. Like my kids in pre-cal, they call this sin. They call it sine.
Wait, what?
3 sin, yeah, sine. And then cusk. We're barely doing the proofs, trig proofs, and yeah. All right, so I do have some of the trig stuff here from pre-cal, and sine and cosecant. After you have done this a while, you can see that they cancel each other. The reason being is because cosecant is 1 over sine, and the reason, the way I teach my kids is that the opposite of this c is s, so it's 1 over sine. So if you were doing secant, the opposite of s is c, so it's 1 over cosine. So that's kind of like my way of teaching them to recall this. So this becomes sine theta 1 over sine theta, because cosecant is 1 over sine, and sine cancel. So eventually this just becomes the integral of 3 sine theta plus 1 d theta. This is not 0, people. And then we can just do this on the fly. The antiderivative of what is sine? Negative cosine theta. That 3 doesn't really impact this. Put it there. And the antiderivative of what gives me a 1? If this had been x's, it would just be x. But these are thetas, so we throw in theta plus chocolate. Why is this negative?
Yeah.
Because the derivative of cosine is negative sine.
Oh. Yeah.
It does take a while. You forgot you were doing it backwards, right? Yeah. In the beginning, you might not like doing it backwards, but eventually you're going to get really good at doing it backwards. Maybe we should have somebody come and do it on the board so it can come out on the video. Dull, right? You have this for, you can show this to your children, you know. Oh, you go to YouTube and they'll see you doing all this crazy stuff. Think about it, right? When I was young, look, son. Eating some almond chocolate. I'll be dead by then, but you know, because you're gonna be 70. I mean, I don't know. The way technology is going, you know, I might pull it off. Yeah. No, we all have to. When I look at George Bush, you see how old he is, right? George Bush, father. Yeah. I saw this video where he tried to stand up, right? Because they were doing, I think they were celebrating his 90th birthday, something like that. He tried and then he just couldn't. He just went, boom, back to the chair. Yeah. But now I didn't think about it. But in my family, I met my mom's grandmother. So I used to play with her. So she died when I was about 8 or 9 years old. So she made it to 103. And her brother made it to 101. And there's some family members in there in the 96, 97 right now, and they're still rolling. Yeah, so they wake up at 4 o'clock in the morning, 3 o'clock in the morning. But at 7 they're already.
Yeah, my grandma in Mexico, she goes to sleep like at 4 in the afternoon. And she starts barriendo like at 4 in the morning.
Yeah.
Yeah.
Everything is dark. What are you doing? What? We're making breakfast.
Monica, you're gonna have to speak English. We have-
You live long when you get very young.
Huh?
We have one over here too.
Oh,
Oscar's in Mexico, he knows about it. Like,
Yeah, the sidewalk, everything.
he just has it.
It's a requirement.
All right, cosecant times cosecant minus cotangent. After you've done this a while, you can kind of just smell the answers miles away. That's cosecant squared. The antiderivative, the derivative of what is cosecant squared? Negative cotangent, so I can see that coming. And then I have cosecant cotangent, and that's related to pist. So that is just cosecant maybe? I don't know. Let me work it out. Yeah. This, the sin of the cusk. Oh, awesome.
So do they call it cot?
Uh-huh.
Do they call it cot?
Oh, the cot. Oh, yes. I have to do that too, yeah. Yeah, but the sin is the one that. Yeah. And then it says sin square. Square your sins. Yeah. So this one is easy. So that one is just cotangent theta. The derivative of cotangent is negative cosecant squared. So it should be negative. All right, so that's done. And then we have cosecant cotangent. So the derivative of secant is secant tangent. So it's related to this one up here, cosecant cotangent. So that should be cosecant. But the derivative of cosecant is negative cosecant cotangent. This is already negative. So this better be a plus. Plus chucklehead. And this is going to be the last problem. Which is really a very tiny introduction to the last topic for the whole year. It's like music to my ears. This topic is actually done with using differential equations. Differentials means, anyway, taking the derivative. So we're giving a derivative here, like a y prime equals 4x. But now we are giving this extra information, which I call the initial condition. Now, what does this mean? Well, it's just extra information about the original function. How this is going to help us is going to allow us to get rid of the chucklehead. So we're going to figure out what the C value is. Right? So if we do the antiderivative of this in a different way, by doing this tiny trick, tiny algebra skill, multiply both sides by dx. We have never, ever done splitting this dy over dx before. So this is the first time. So now you have a dy only equals 4x dx. And you're like, oh, now I see where that dx is coming from. Right? So now what can I do now? Look, antiderivative on both sides. What does that look like? Like the stuff we done just a while ago. You can add 4, 4. You can subtract 4, 4. You can square both sides. You can take the antiderivative on both sides. It's an algebra skill. It's just now we're doing calculus with it. Okay? So what's the antiderivative of this? If this had been antiderivative of dx, what would you have given me? X, right? Because the derivative of x is 1. But the variable that we're messing with right here is an x. That's why you gave me an x. But if I have a y, because this is a dy, the antiderivative of that, it would still be a 1, but it would be a y only. Do we have a chucklehead right here?
No.
Yeah, we do.
Oh, we do?
Yeah, because this is a antiderivative of this. So every antiderivative has a chucklehead. So we have to put plus c equals antiderivative of this. Bump it up, x squared. Divide, 2. Plus chucklehead, right? Now we have a problem here. You cannot call both of them chucklehead, so we'll use Jose's knucklehead, right? So we put a D here, or maybe we can call this one C1 and this one C2, whatever floats your boat. I will go with that, right? Now let's think about this for a bit. Can I do minus C1, minus C1? So that way I can just have the y right here by itself? Will that be legit? That's fine, I think, right? So minus C1, those cancel. So now I have y equals 2x squared plus C2 minus C1. Well, those two things are really numbers. They're constants. Do I call it C3? Do I call it D? You can call it whatever you want. It's still a constant. So we're going to call it C3. Now, I did something really crazy here, which I typically don't do. Typically, when I do antiderivative on both sides, I do not put a chucklehead on this side. Because I already know that this chucklehead is going to move to the other side. And I'm going to end up with how many? Just one chucklehead. So I just put one chucklehead on that side. I avoid doing all this because it's just stuff that is not going to help me solve the problem. Right? It makes the algebra look great, pretty. So this is what I have. That's the antiderivative on both sides with the chucklehead. And you might be thinking, well, where is this coming from? If you graph this, I'm going to erase this, so hopefully you have it on your papers.
No, I can't see.
You need it?
I'm going to graph that, and this is what's happening graphically. What does 2x squared look like? A parabola, right? But you don't know what this value right here is, so let's call it a 0. 2x squared plus 0 is just that right there. 2x squared plus 1 is the same parabola shifted 1 up. Minus 1, minus 2, minus 3, and that's because that chucklehead is giving you the whole family. So the initial condition what's going to do for you is going to tell you, go and look for the one that I want. Go and look where 0 and 6 is. When x is 0, y is 6, maybe it's here. I'm looking for this parabola right here. So I'm extracting a family member of all the antiderivatives. So we're going to go and use that. Y is 6, x is 0, so c is 6. So now my final answer is y equals 2x squared plus 6. And that is that graph right there. So an initial condition allows you to get rid of the chucklehead. In other words, go and look for the specific function of all the functions that an antiderivative provides. How y'all feel? Good? Y'all got this? All right? All right, so here we go. Given a derivative, 6x squared, with the initial condition f of 0 equals -1, we're going to figure out what the original equation is. So we're going to separate this derivative. Here we go. dy over dx equals 6x squared. So we're going to multiply both sides by dx. dx, booyah, gone. So dy equals 6x squared times dx. So after we have separated this, we can take the antiderivative on both sides, and the antiderivative of dy is just plain y. Okay? And for the antiderivative of this, we do have a chucklehead right here, but we're not going to put it because we're going to cram all chuckleheads in one side, right? Constant c's. Bump up this one, that will get you a cube, and then divide, so 6 divided by the 3, after you have done the bumping up, you get a 2 plus c. Now the initial condition comes in. Remember, this is f of x, which is the same thing as y. If that creates a problem for you, you can always replace this with the f of x. So that way that you can see that you're plugging in the 0 there. F of 0 is a -1 according to the initial condition. So that's a 0. So is that just c? I found the c. Once you find the c, you plug it back into the equation that you derived after taking the derivatives. So f of x equals to x cubed minus 1, and that is our final answer for this problem. That is the one that will meet the requirement of having this initial condition. Are we good? You all got this? Yes?
Oh, no, that's because I keep yawning.
You can't breathe?
No, it's because I keep yawning.
Come again?
I keep yawning.
Oh, it's okay. I mean, we're not here to judge. Foz keeps wondering. I'm teaching, he's like, the chicken or the egg? You know, in a way, I don't want you to drop the class because it's, you know, who am I going to pick on? You know,
Yeah. You find somebody else.
Find somebody else? I always find somebody else, but I like you, so. All right, so now we're going to apply this concept to a PVA problem, position, velocity, acceleration. So in this scenario, we have a person throwing this ball upward from a height of 6 feet with the initial condition of, with the initial velocity of 60 feet per second. And the question is, how high is the ball going to go, right? So can somebody give me some type of idea of what's happening here? Because they say, you know, from a height of 6 feet.
That's what it's the crippling. That's a chucklehead.
Huh?
Would that be a chucklehead?
No, well, I'm just trying to get like a diagram of of the scenario that's happening here. Right, let's say that here's the ground, right? Here's the person.
Does that mean the person is like 6 feet tall, so they're throwing the ball from like 6 feet up?
Right. Well, that could be a possibility, right? Maybe he has the ball and then he throws it room. So this height will be 6 feet, right? So you have to take that into consideration, right? So that would be one possibility, the ball going all the way up and then coming back down. So the question is, how high is the ball going to go from the ground, right? So that's kind of tricky, but how we're going to use antiderivatives on this problem? I mean, the concepts that we learned. How high is the ball going to go? So it's really an acceleration, velocity, position. What is that? How high is the ball going to go? It's a position type of thing, right? But we don't have positions here. What we have right here, we have an initial condition for velocity, we have an initial condition for position, and we have a function for acceleration. That's not an initial condition because that's a t right there. So this is the process that we're going to go through. We're going to take the antiderivative of a of t. Why? To go back to v of t. Now, when you take the antiderivative of a of t, you'll get v of t, but that v of t will also have a chucklehead attached to it, right? So we're going to have to figure out what the c is, and we're going to use the initial condition of velocity to figure out that c. We're going to replace that c, and that will give us that particular function v of t. Then we're going to take the antiderivative of v of t, and we're going to derive s of t. but we're going to get another chucklehead right there. But we're going to use the initial condition for position, and we're going to replace or find that other chucklehead. Once we get that position function, then we can answer questions about position, which is sort of the question that is being asked in this problem. How high is the ball going to go? Do y'all see what we're going to go through right now? All right. So let's erase this right here and create some space. And I'm going to just have that up there because I need some space. All right, so I'm going to say velocity of t is equal to the antiderivative of a of t dt. So velocity equals the antiderivative of negative 32 dt. Where did I get this negative 32 from? It's the function. There it is. Right? So velocity equals the derivative of what is negative 32? Negative 32t plus c. And we're going to use v of 0 to figure out that c. So v of 0 equals negative 32 times 0 plus c. V of 0 is 60. 60 equals negative 32 times 0, which is really 0, and that is just c. Found my c, and it's going to be replaced into the v of t function. So v of t done. I found v of t. Now we're going to go through the same process, and we're going to go and figure out what s of t is. S of t equals the antiderivative of v of t, dt. So S of t equals the antiderivative of, I'm going to replace my v of t with negative 32 plus 60 dt. Be careful here that dt does belong to both terms, so you have to encapsulate that in parentheses. Antiderivative of negative 32t, you would need to bump up the t, that becomes a t squared, and then divide 32 by 2, so you will get negative 16t squared plus 60t plus c. Now we just need to find the c for the position function, and that's where that comes in. Right? So S of 0 equals negative 16 times 0 squared. S of 0 is 6. 0, 0. My c is 6. I found the c. C will replace that c in there, in that particular function. So S of t Are we good? Okay. So now you're like, okay, we've done all this work, and how do I get the answer? Well, we know a lot of stuff right here. I can figure out the velocity at any given time. I can figure out the position at any given time. So now I just need to connect the dots on what's happening with the scenario, right? Now remember that we did have this person throwing the ball. Up and then down. Now, what's the velocity of the ball right here when the ball is in my hand? I'm about to throw it up. 0. It goes up, 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 up. What's the velocity right there when it reaches the top?
Zero.
It's 0. This is really a turning point too, right? So, and the velocity when it hits the ground is also 0. So there's something about velocity being 0 that is critical point. So we're going to go and figure out when the velocity is 0 by taking the velocity function and setting it equal to 0. All right, so 0 equals negative 32 t plus 60. So 60 divided by 32 equals t. T equals 15 divided by 8. What does that mean though? Yeah, that the velocity is 0 at that time. Which time is that? Is that the time when it's in my hand, the time when it's on the top, the time when it's hitting the ground? What is it? When it reaches the top. Exactly. Very good. So now we know when it reaches the top. So how high does it go? Plug it into S of t, and that will give me the position at t equals 15. Now here's a quick question for you. It will give me the distance from my hand all the way up to how high it goes. Or will it give me the distance from the ground all the way up to the top? From the hand?
No, from the ground because you have a plus 6.
Excuse me?
You'll see the distance from the ground because the initial condition is plus 6.
The initial condition is plus 6.
Well, like you throw it from 6 feet high, measure it from the ground.
Right. Did you understand what he's saying? When time is 0, where's the ball? 6. So is it on the ground? No. But when the time is 15 divided by 8,
It's at the top.
it's going to be at the top. So whatever value I get from the after I plug in 15 divided by 8 in here, is that value that I'm getting there? Is it a distance from my hand all the way up to the top, or is it from the ground?
Oh, I understand what you're saying.
In other words, after I compute this answer, let's say that I plug in 15 divided by 8 in here, and I'm making up a number, 20. Okay, so this distance is 20. Now, does it mean that it's 20 from here all the way up to the top, this whole distance, or does it mean that it's 20 from here to the top? And then I have to add this 6.
From the ground to the top.
That function will give me the distance from the ground?
I think it'll give it from the hand.
From the hand? Well, he kind of said it. He kind of gave the answer right away. What is the position of the ball when time is 0? 6. So that function is giving you the height from the ground already, all right? So you don't have to add this 6 to your final answer.
But it's already added on like that.
Yeah.
Yeah. It's already given to you in the initial condition. They already took that into consideration. Did you understand that, Lupe? Okay, very good. So we're just going to plug in. And I'm not going to compute this. It's just algebra for that one. So that would, whatever answer this gives you after you simplify, that would be your final answer. But did you all see what the process that we went through? It's a really good problem because you have to, to do the antiderivative 2 times. And it's a PBA problem. It seemed really complicated, but it's really not that big of a deal. Except for that little twist right there.